Section 10.1.2, Executing the chi-square test for one-way tables, goodness of fit. What we're going to start with is measuring deviation. Recall from lesson 10.1.1 that cereal manufacturers want to have a product that will be well received by children and their families. A market research company conducts a cereal consumer feedback survey to learn whether consumers would be likely to purchase a specific type of cereal again. The market research company randomly asks a sample of consumers who have purchased the cereal. The company asks these consumers, based on your family's experience with this box of cereal, would you be likely to purchase this cereal again? Yes, no, or maybe. Assume that the market research company has determined through other research that the ideal distribution of responses in the population of cereal consumers would be the following: 65% saying yes, I would likely purchase this cereal again, 25% saying no, I would not likely purchase this cereal again, and 10% saying maybe, I am not sure if I would purchase this cereal again. The company would care about any significant deviation or difference from this ideal population distribution, because such deviations imply that the cereal may need better marketing, some product adjustment, or less expensive advertising methods. In other words, if the observed distribution differs from the desired distribution in a statistically significant manner, the cereal manufacturing and the marketing company handling cereal sales need to take action. So the analysis method that we look at is called the chi-square goodness of fit. You can kind of think of this phrase, goodness of fit, as how good does our observed model fit the expected model. The analysis of certain categorical variables requires inference techniques that have not been discussed in previous modules. One of these inference techniques is this chi-square goodness of fit test. The logic and steps involved in the chi-square goodness of fit test are very similar to previous hypothesis tests that you have studied. So if they're similar to the hypothesis tests, let's start with the null hypothesis. For a chi-square goodness of fit test, the null hypothesis H0 states that the categorical variables population is distributed as expected. You can see in that statement there is no change. They are distributed as expected. That's why it's going along with the null hypothesis. In other words, the null hypothesis is that the population proportion for the first category will equal a specified desired value, and the population proportion for the second category will equal a specific desired value, and so on. The null hypothesis is typically written as H sub 0 equal pi sub 1 equal to a hypothesized proportion for the first category. So for example, 0.65 going along with the 65% that said yes. Pi sub 2 equal some hypothesized proportion for the second category, and so on. And if you haven't seen that symbol before that they're writing there, pi, that's another Greek letter. And it's just a variable. It doesn't mean what you might have seen as a number for pi. It just means a letter, just like if you used lowercase p. The alternative hypothesis, H sub a, states that the categorical variables population is not distributed as expected. The alternative hypothesis is typically stated in words, sort of like we saw in the ANOVA section, and it uses one of the following sentences. You could say for the alternative hypothesis, H sub 0 is not true, meaning the null hypothesis is not true. You could say for the alternative hypothesis, the population is not distributed as stated in the null hypothesis. And then the alternative could also be said, at least two statements in the null hypothesis are not true. So let's start with number 1. What is the null hypothesis for the cereal consumer feedback survey case that was introduced at the beginning of this lesson? Use the notation pi with a subscript yes to represent the population proportion of consumers who would say yes, I would likely purchase this cereal again. Use the notation pi subscript no to represent the population proportion of consumers who would say no, I would not likely purchase this cereal again. And use the notation pi subscript maybe to represent the population proportion of consumers who would say, maybe, I am not sure if I would purchase this cereal again. So, all we are doing is stating what each of these population proportions are equal to. And so we were given, back on the previous page, from their market research, they had 65% that would say yes. So what they expect to see is pi with a subscript yes is equal to 0.65, just converting the percent into a decimal. The population proportion for those that say no, that would be 25%, which is 0.25, and then pi with a subscript maybe, that's the 10%, which is 0.10 as a decimal. And then number 2, what is the alternative hypothesis for the serial consumer feedback survey case? Again, we can use any one of the 3 that are up above. The one that I like to use is the second one. And the reason why is because at least it gives us a little bit of context. The population is not distributed like we see in the null hypothesis. So the population is not distributed as stated in the null hypothesis. So as stated in H sub 0. So moving on, keep in mind that the chi-square goodness of fit test does not examine a claim about a single category's proportion. Rather, the chi-square goodness of fit test examines whether every claim regarding a proportion in the distribution seems plausible. Conditions. In order to be able to conduct a chi-square goodness of fit test, the following conditions must be met. As we've seen many times before, the sample must be random, and also each expected count must be at least 5. Expected count being at least 5, that's again going back to the idea of sample size. As you saw in the previous lesson, in a chi-square goodness of fit test, the expected count for a given category is the desired population proportion for that category, pi sub 1, for instance, multiplied by the sample size n. In other words, the expected count for category 1 is n times pi 1. The expected count for category 2 is n sub pi 2, and so on. When calculating expected counts, keep in mind that they do not have to be whole numbers. In other words, they can be non-integer values, so things like decimals. You should generally not round expected counts to whole numbers. As a check of your counts, make sure that the sum of your expected counts equals your sample size. So to see how that all works, number 3. For the serial consumer feedback survey, would a random sample of 205, meaning n equal to 205, consumers satisfy the conditions for executing a chi-square goodness of fit test? Why or why not? So let's look at the following. The expected yes. That would mean take our sample size n and multiply by the pi sub yes value. So that's 205 times what we said pi sub yes was equal to, 0.65. And when you multiply those two numbers, you will get 133.25. That's above 5, so far so good. Then how about the expected no? That would be the sample size n times pi sub no. So that's 205 times 0.25, which is 51.25. That's also greater than 5, so still doing well here. So then finally the expected maybe, that would be our sample size n times pi sub maybe, which would be 205 times 0.10, so 10% of 205, and that is 20.5. Since all 3 of these are greater than 5, then we have that condition met. So when they ask would a random sample satisfy the conditions, we've got the sample size is good, and then they do say that the sample is random. So we've got all three of our expected counts are greater than 5, and the sample is random. So the whole answer for number 3 would be yes, and the reasoning is what I just wrote below. Okay, we've seen things like this before when we talked about proportions. It's the same idea. Number 4, for the same survey, would a random sample of 46 consumers satisfy the conditions for executing a chi-square goodness of fit test? Why or why not? So they've made the sample smaller. It's still random, so we've got that condition. But n here is 46. So again, you would look at, well, what is 65% of 46? What is 25% of 46? And then what is 10% of 46? And if you find out what 10% of 46 is, that would be 4.6. So we run into a problem. 10% of 46 is 4.6, which is less than 5. So the expected maybes is too small. So that's an example of a sample size being too small. So they definitely want to have something large enough where all of those expected counts are large enough. All right, once we have those conditions met, then we get to computing the chi-square test statistic, which we did see in the previous lesson. For a chi-square goodness of fit test, compute the chi-square test statistic in the same manner as shown in the previous lesson. Number 5, suppose that a random sample of 558 consumers responds to the serial consumer feedback survey as follows. 382 say yes, 128 say no, and 48 say maybe. Compute the chi-square test statistic and fill in the table below. For steps 3 and 4, calculate the statistic to 3 decimal places. So moving on to our table on the next page, first we have the observed counts. This comes from the sample. So from the paragraph in number 5, it says that they observed in their sample 382 saying yes. So that would be 382. And then 128 said no. And then 48 say maybe. Then we need the expected counts. Now we don't have these calculated yet because notice the sample size here is 558, which is not the same thing that we had in numbers 3 or 4. So we're going to have to do the same thing that we did for number 3 again here. So we can do this. Expected yes, that would be the sample size 558 times the percent that we expect for yes, so 0.65 as a proportion. And when you multiply those two numbers, you get 362.7. So that goes in the row for expected count for yes, 362.7. Then we next need to find the expected no. And that would be, again, the sample size 558 times 0.25. Multiplying those two, we're going to get 139.5. So that becomes our expected no. And then the expected maybe, that would be the 558 times 0.10, and that's 55.8. So just like we saw in the previous lesson, the next step is subtracting. So here we take our observed count and then subtract the expected count. So for the yeses, that would be 382 minus 362.7. So that gives us a difference of 19.3. And then for the no's, 128 minus 139.5. That gives us negative 11.5. And then for the maybe, 48 minus 55.8, that's a negative 7.8. Then the next step is to square. So we have to take each of those numbers that we just got and multiply them by themselves. So 19.3 squared, that gives us 372.49. And then for the nose, we would take parentheses negative 11.5 and square it, so we don't forget that a negative squared will give us a positive. That gives us 132.25. And then for the maybes, parentheses negative 7.8 squared, that gives us 60.84. So now to get step 3, we take where we just left off, the row that we have for step 2, and we have to divide by the values that were our expected counts. So for the yeses, that means that I need to take 372, and I'll write this off to the side so you can see. I have to take for step 3, 372.49, and I have to divide by the expected count, which was 362.7. And remember from the previous page, they said when we do this, 372.49 and divide by 362.7, we need to then round to 3 decimal places. So that gives us 1.027. So then for the nose, I take 132.25. That was the step 2 answer for the nose. And then I have to divide by the expected count, which was 139.5. So 132.25 divided by 139.5. And rounding to 3 decimal places, that gives us 0.948. And then finally for the maybes, that would be 60.84 divided by the expected count for the maybe, 55.8. So 60.4 or 84 divided by 55.8 gives us 1.090. So then for step 4, remember from the previous section, we add up the values that we just got in step 3. So that would be 1.027 plus 0.948 plus 1.090. So 1.027 plus 0.948 plus 1.090, and that gives us 3.065. And so that becomes our chi-square value. Okay, so we just found a test statistic for a hypothesis test. You can think that what comes next is a p-value. In previous lessons, we have studied hypothesis tests that use a z or t test statistic. For a chi-square goodness of fit test, we use the chi-square test statistic to calculate the p-value. The methods for estimating and computing the p-value from a chi-square distribution will be discussed in detail in the next lesson, 10.1.3. But for now, let's take a look at these questions. Number 6, which provides stronger evidence against a null hypothesis? A small p-value or a large p-value? You might have remembered from before, if the p-value is less than alpha, that means you reject the null hypothesis, which means there would be evidence against the null hypothesis. So, small p-value, that means reject the null hypothesis, which means you have evidence against the null hypothesis. Number 7, in the previous lesson, you saw that larger chi-square values provided stronger evidence against the claim that a population is distributed as expected or desired. Do you think that a large chi-square test statistic will correspond to a large p-value or a small p-value. Explain your reasoning. So if we think about what we saw in the previous section, when you have a large chi-square value, it means that you have evidence against the population being distributed as expected or desired. So the population being distributed as expected or desired, that's what your null hypothesis says. So a large chi-square, that provides stronger evidence against the null hypothesis. And if we just said number 6, that a small p-value also says the same thing, that means that a large chi-square value is connected to a small p-value. And this is exactly the same thing that we saw with t-test statistics and z-statistics. Larger z-scores, smaller p-value. Larger t-scores, smaller p-value. Same exact concept. You even saw this in ANOVA. When you had a larger f-test statistic, there was a smaller p-value. Number 8, the chi-square test statistic that we just got, 3.065, is not considered a large chi-square value. We're going to see why when we get into the next section, but we'll just take that at face value. So if it's not considered a large chi-square value, do you think that this chi-square test statistic will correspond to a large p-value or a small p-value? Explain your reasoning. So here, if they're saying that it's not large, then if it's not large, it means that it's small. Right? That's the opposite of large. And if we just said that large chi-square values are connected to small p-values, then we have the opposite here in number 8. So that means that small chi-square, those correspond to large p-values. Again, same thing that we saw with z-scores, t-scores, and f-test statistics. So this is just the opposite of number 7. So then finally, deciding and concluding. The rule for determining whether to reject the null hypothesis in a chi-square goodness of fit test is the same as for other hypothesis tests. Reject the null hypothesis if the p-value is less than or equal to alpha, where alpha is the significance level. Number 9, the p-value associated with a chi-square test statistic of 3.065 based on a categorical variable with 3 categories, such as in this serial consumer feedback survey case, is fairly large. In fact, we'll be able to figure that out in the next section, but the p-value is more than 0.20. At a 5% level of significance, would you reject the null hypothesis? So, if the p-value is more than 0.20, then the p-value is definitely more than alpha, which is 0.05. Right? If you have more than 20 cents, then you still also have more than 5 cents. Whenever we have the p-value being greater than alpha, that tells us to fail to reject the null hypothesis. So, no, we would not reject the null hypothesis. We would fail to reject the null hypothesis. And then number 10, in questions 1 and 2 of this lesson, you recorded the null and alternative hypotheses for the serial consumer feedback survey case. Remember that if the observed proportions differed from the desired proportions of 65% yes, 25% no, and 10% maybe, In a statistically significant manner, the cereal manufacturer and the marketing company handling cereal sales need to take action. Based on the random sample introduced in question 5 and the decision you made in question 9, do you think that action is needed? Well, what we just decided in number 9 is we fail to reject the null hypothesis, which means we didn't reject the null hypothesis, which means we don't have evidence against the null hypothesis. So, is action needed? No. No. We fail to reject the null hypothesis. So the evidence does not suggest that the proportions are different in a statistically significant manner. This does not provide evidence that things are different than what they have claimed, so it doesn't seem like action is needed. So here's the steps for what we just did in this goodness of fit test. Similar to what we've seen with hypotheses tests, state the null and alternative hypotheses, state the conditions, and examine if they are met, compute the chi-square test statistic, compute or approximate the p-value, and then finally decide and conclude. And now that we're at the end of this lesson, the secret word for this lesson is maybe.